In examples 15 and 16, we want to start looking at applications of exponential equations. Specifically in example 15, we assume we invest $11,262 in an account, earning 4.14% per year compounded continuously. We want to use Wolfram Alpha to complete the following. There are different investment formulas, but what we're looking for specifically in this case is this language that our investment is compounded continuously. If that's the case, then we know that our final amount at the end of our investment is going to be equal to the principal, the original amount that we invest, times E raised to the R, where R is the investment rate, times T, where T is the time in years. So since it's being compounded continuously, we can use this formula. What we want to know first is how much will we have left in our account after 10 years? Well, that means we want to take that formula and plug in our given values. We're investing an initial amount, P, of $11,262 times E, we just type the letter E, and then raise that inside a set of parentheses to 0.0414 times 10 years. So that's our interest rate times 10 years. So after 10 years, if we get more digits here, our result will be $17,037.80. And then in part B, we're asked how many years will it take for your investment to grow to $19,285. Now we have a slightly different problem because what we're looking at is finding how many years it will take. So instead of in part A, capital A was the value we were after, now T is going to be the time that we're after. That means we want to solve our final amount of $19,285 equal to the original investment, $11,262, E to the same interest rate, 0.0414, times T. We're leaving T as the unknown because that's what we're trying to solve, what we're trying to answer. And then we'll get a result that has an I in there. We want to ignore anything that has an I because we're not worried about complex results. We're looking for the real solution, and in an approximate form that would be 12.99 or about 13 years. In example 16, we have an asset that was valued at $83,695.72 in 2020. This year, the value depreciated to $48,827.87. We want to use Wolfram Alpha to complete the following. First thing we want to do is find the rate of depreciation of the asset. In this case, we're going to use the same formula that we used above. A is equal to P E to the RT, where P represents the original amount, A represents the amount that the asset has depreciated to after T years, and it's depreciating at some rate R. This is exactly the same formula that we used in example 15, but now what we're looking at is a case of exponential decay because our asset is decreasing in value. That value for A is going to decrease over time. So the difference here is that our value for R is going to be something less than 0. The other trick to this is that we need to figure out after how many years did it take the asset to depreciate to $48,827.87. We're given the language this year, meaning the answer to this problem is going to vary depending on when you're actually working this question, but I'm working on it in 2024. the original value of the asset was from 2020. So the value for t that we're going to want to use is 4. A year from now, that would be 5, and so on. So what we're going to do is solve the final value this year, which is that 48,827.87, is equal to the principal, which was the original value of the asset in 2020, e to the raised to the r times t power, where t is going to be 4. And here we're letting r be that unknown value because what we're trying to find is the rate of depreciation. So for some reason Wolfram Alpha didn't like my input at first. I paused my video and off screen that you couldn't see, reloaded the page and entered this in. Again, it did give me the answer I wanted, so I'm going to assume that was a temporary glitch. Again, we get a result. The first one is in terms of I. We want to skip that and look for the real solution and get this in approximate form. So we get a negative value for r, which makes sense. The value of our asset is decreasing. So the rate of depreciation, our value for r that we got, is negative 0.1347. But in terms of actually reporting our depreciation rate, we would want to say that our depreciation rate is 13.47%. In that case, we drop the negative sign as we report that, because depreciation already implies the negative value for r. In part B, if the asset's value continues to drop at that same rate, what will it be worth in 2032? So 2032 minus our original year of 2020 means we're going to plug in a value for t of 12. So we'll enter that original value of the asset in 2020 and then raise e to the negative 0.1347. That's our negative interest rate, or negative rate of change, times 12. To get $16,623.01.